the Antikythera Mechanism. In 1901, off the coast of the small Greek island of Antikythera, sponge divers searching for sunken treasures stumbled upon the shattered remains of an ancient Roman shipwreck resting 200 feet beneath the waves. Among the statues, amphorae, and debris, one object stood out, a lump of bronze encrusted with centuries of salt and marine life. It was dismissed as scrap until it split open and revealed an intricate network of gears, dials, and inscriptions. Over a century later, that artifact is now known as the Antikythera Mechanism, and to this day, no one fully understands how it was made. The device was later dated to between 100 and 200 BCE, but its capabilities defy the logic of that era. As researchers began carefully reconstructing its fragments using X-ray tomography and surface imaging, they discovered a gear system so precise it mimicked the movements of celestial bodies, the sun, the moon, and the 5 visible planets. It could predict solar and lunar eclipses, track the 4-year Olympic cycle, and account for the 19-year Metonic cycle, which links the lunar and solar calendars. The mechanism contains over 30 interlocking bronze gears, each finely cut with triangular teeth, a design standard thought to have only emerged during the European Renaissance, nearly 1,400 years later. The largest gear alone had 223 teeth and was precisely calibrated to interact with multiple secondary systems, including a differential gear that modeled the irregular orbit of the moon, a concept that wasn't formalized until Isaac Newton's Principia. The level of craftsmanship implied the use of tools capable of cutting gear teeth with sub-millimeter accuracy, an achievement that modern watchmakers still struggle to replicate without digital assistance. One gear had a tooth pitch so fine it suggested the use of a dividing engine, a tool no one believes existed in the ancient world. The device wasn't a toy nor a decorative artifact. It was an analog computer. As more fragments were recovered, scholars noticed the inscriptions on the mechanism's bronze surfaces. Written in Koine Greek, they referenced complex astronomical cycles and mechanical functions, including phrases like eclipse indicator, moon phase, and calendar pointer. The text covered everything from the Saros eclipse cycle to planetary synodic periods. The mechanism could not only tell you when an eclipse would happen, but whether it would be lunar or solar, and in which direction the shadow would move across the Earth. Yet, perhaps more unsettling than the mechanism itself is what followed its discovery. For decades, the object was quietly kept in the National Archaeological Museum in Athens, barely mentioned in academic circles. Early attempts to study it were stifled by lack of funding and inexplicable institutional delays. Photographs and internal memos from the 1950s went missing from archives. Several key fragments have never been recovered from the seabed, and exploration permits to revisit the site are notoriously hard to obtain. Some historians have questioned whether the Antikythera mechanism is truly a one-off, or if it was merely the only survivor of a much larger, now-erased lineage of advanced Hellenistic engineering. If it were mass-produced or widely known at the time, why is there no record of similar devices elsewhere in ancient texts, libraries, or ruins? The implications are staggering. If ancient civilizations possessed analog computers capable of tracking planetary orbits and eclipses with machine-like precision, then the timeline of scientific advancement as we know it collapses. Either the Greeks achieved a singular technological breakthrough that vanished overnight, or they inherited knowledge from an even earlier, forgotten civilization. And if so, who erased that knowledge, and why? The Baghdad Battery. In 1938, Wilhelm König, director of the National Museum of Iraq, was cataloging artifacts from an excavation site near Kujut Rabu, southeast of Baghdad, when he stumbled upon a puzzling clay jar. It was unassuming, just over 5 inches tall, with a narrow neck and sealed with asphalt. But when he opened it, he found a tightly fitted copper cylinder inside, capped with a corroded iron rod. It resembled no ceremonial or storage object of its time. König proposed something unthinkable. It was a galvanic cell, in short, a battery. The so-called Baghdad Battery dates back to the Parthian or Sassanid periods, between 150 BCE and 250 CE. When replicas were filled with vinegar, lemon juice, or grape juice, they produced a steady voltage of around 0.5 to 1 volt, enough to power low-current applications. Its internal components, an iron rod suspended within a copper tube, all encased in a clay pot, mimicked the design principles of modern dry cells, predating Alessandro Volta by nearly 2 millennia. Some argued it could have been used for electroplating, depositing a thin layer of metal onto another surface, as early 20th century German experiments demonstrated that the device could gold plate small objects. But there's no archaeological evidence of plated items in nearby digs. Others speculated it may have been used in religious rituals, possibly to shock participants during oracles or healing ceremonies, giving the illusion of divine power. Physically, the artifact was sophisticated. The copper cylinder was rolled from a thin sheet with minimal overlap, showing knowledge of metallurgy. The iron rod was carefully centered to avoid touching the copper directly, allowing a liquid electrolyte to serve as the conductive medium. The bitumen seal prevented evaporation, a level of chemical foresight rarely credited to ancient peoples. Despite these functional clues, mainstream academia hesitated to embrace the idea of ancient electricity. The battery theory was criticized as fringe, even though physical tests repeatedly supported Koenig's hypothesis. Meanwhile, several similar artifacts surfaced. Not exact duplicates, but jars with comparable internal metal assemblies. None were ever displayed prominently in museums. Some vanished into private collections. Others were locked in storage, rarely studied again. Iraqi government documents from the 1970s show that follow-up excavations at Kujut Rabu were halted after just a few weeks, with no official explanation. Requests to re-examine the original dig site in the 1990s were denied due to security concerns. Western archaeologists visiting the region reported missing paperwork, mislabeled crates, and restricted access to museum storerooms. Why would a seemingly minor artifact spark such institutional resistance? If ancient civilizations did harness electricity, even in a primitive form, it rewrites the technological baseline of the ancient world. It suggests a knowledge network, a science of materials and energy that somehow emerged and disappeared without a trace. And that erasure raises troubling questions. Was this knowledge lost to war, conquest, or deliberate suppression? Or was it never meant to reach modern eyes in the first place? The water clock of Karnak. In 1904, while excavating the temple of Amun-Ra at Karnak, Egyptologist Georges Legrain discovered a large carved stone basin, unlike anything else in the complex. At first glance, it appeared ornamental, perhaps a font or offering bowl. But inscribed along its interior were a series of evenly spaced markings, accompanied by a grid of vertical columns and hieroglyphic notations. What Legrain had found was no ritual vessel. It was a highly advanced clepsydra, a water clock, engineered to track time with extraordinary precision over 3,000 years ago. Unlike sundials, which falter in darkness or poor weather, the Karnak water clock operated continuously day and night. It relied on a steady flow of water from a small reservoir into the carved basin. As the water level rose, it passed the marked gradations, each corresponding to precise intervals of time. Some versions were designed to function in reverse, draining water at a calibrated rate. This wasn't a crude estimate of time. It was a mathematically measured device, capable of subdividing the night into 12 equal parts, even as night lengths shifted with the seasons. Hieroglyphs carved into the basin provided both time markers and astronomical references. Scholars later interpreted these symbols as links to star positions and lunar cycles, suggesting the clock was used not only for scheduling rituals, but also for celestial alignment. The inscriptions showed a deep awareness of sidereal time and the solar calendar, and may have been part of a larger system that synchronized the temple's operations with cosmic events. What made the Karnak clepsydra even more astonishing was its apparent calibration system. Microscopic studies revealed that the inner surface had been polished to near uniform curvature, allowing for a controlled, consistent rise of water. The flow rate was regulated through narrow spouts, some just a fraction of an inch in diameter, too precise for tools believed to exist in Egypt at the time. Experts from the 20th century attempting to recreate the design found that even minor deviations in angle or spout width threw off the timing by several minutes per hour. But the original, it had a maximum deviation of less than 30 seconds per hour. This level of precision suggested not only advanced engineering, but repeated testing, as if ancient priests or architects had fine-tuned the device over generations. Similar stone clocks were later found in other Egyptian temples, some dating as far back as the 16th century BCE. The implication was clear. Karnak's water clock was not a standalone innovation. It was part of a systematic timekeeping tradition that flourished long before mechanical clocks ever ticked in Europe. Yet outside academic papers, this discovery remained largely unknown to the public. Museum plaques labeled it simply as a ritual basin. Popular history books rarely mentioned Egyptian water clocks, focusing instead on sundials and shadow casting. Attempts to fund full-scale reconstructions were denied by major institutions, citing lack of historical significance. The clepsydra, despite being one of humanity's earliest and most accurate timekeeping devices, was quietly sidelined. Why? Perhaps because acknowledging its sophistication would force a revaluation of the scientific literacy of ancient Egypt. Not as a land of superstition and tombs, but as a civilization of precision engineering and empirical calibration. The Karnak water clock didn't merely tell time, it encoded astronomy, seasonal shifts, and sacred alignment, all in a carved bowl of stone. And if a culture 3,000 years ago could master fluid dynamics and astronomical timekeeping without a single cog or gear, what else have we misjudged? The Viking Sunstone. In 1948, deep within the icy ruins of an 11th century Norse settlement in Greenland, archaeologists uncovered a small, unremarkable disc carved from calcite. Initially dismissed as a decorative object or tool fragment, it was placed in storage with minimal documentation. It wasn't until decades later, when researchers revisited Viking navigation techniques, that the true significance of the artifact came to light. What they had found was likely a solar stein, a sunstone, a crystalline navigation tool that may have allowed Viking sailors to cross the Atlantic with stunning accuracy, centuries before the invention of the magnetic compass. According to Icelandic sagas, Norse navigators used a mysterious sunstone to determine the position of the sun on cloudy or foggy days. For generations, this claim was treated as myth, but the rediscovered artifact, along with others found in shipwrecks and trading posts, suggested a different story, one grounded in physics. Modern experiments demonstrated that certain crystals, notably Iceland spar, a form of calcite, can polarize light. When held against the sky, even under cloud cover or near twilight, the stone reveals a distinct glow or shadow when rotated, pointing toward the sun's true position. This optical property, known as birefringence, splits incoming light into two paths. By aligning the stone until the two beams equalize, a trained navigator could determine solar azimuth with surprising accuracy, often within a few degrees. Further supporting evidence came from a 2013 discovery, a calcite crystal recovered from a 16th century English shipwreck near the Channel Islands. Tests confirmed that the crystal still exhibited effective polarization. Centuries underwater had not dulled its properties. If Renaissance sailors carried sunstones, could Viking explorers have pioneered the technique 500 years earlier? Researchers at Eötvös Loránd University in Hungary conducted blind navigation trials using reconstructed sunstones and found participants could estimate the sun's position within plus or minus 2.5 degrees, even in fully overcast conditions. That level of precision, when used with a known time of day and consistent sailing direction, could guide ships across thousands of miles of open ocean. Given the treacherous and fog-laden North Atlantic, this would have been not just useful, it would have been essential. Yet, despite mounting scientific validation, the idea of Norse optical navigation remains largely excluded from standard history books. Critics argue that there is no definitive Viking manual or toolset referencing the stones directly, but absence of documentation isn't proof of non-existence, especially in oral cultures. The Greenland Sunstone, now held in a Copenhagen museum, remains unlabeled as a navigation tool. Visitors pass by it without ever learning it may have enabled transatlantic travel centuries before Columbus. Why the reluctance to explore this narrative? Because if the Vikings used polarized light to navigate, they weren't just rugged seafarers. They were optical physicists in leather and fur, wielding natural crystal tech that wouldn't reappear in European science until the 17th century. And if they mastered light manipulation for navigation, what else did they know about the forces around them? The Archimedes Mirror. In 212 BCE, as the Roman navy laid siege to the Greek city of Syracuse, An unusual defense was reportedly unleashed from its fortified walls. According to later accounts by ancient historians like Lucian and Galen, a group of Roman warships caught fire without any catapult or flaming arrow in sight. The source? A strange assembly of polished bronze mirrors allegedly arranged by the famed mathematician Archimedes, designed to focus sunlight into a beam so intense it ignited enemy sails from a distance. For centuries, this account was treated as apocryphal, a tale too fantastical to be true. But repeated modern experiments have forced a re-evaluation of this solar weapon. In 1973, Greek engineer Ioannis Sakis recreated the setup using 60 polished bronze mirrors, each about 3 feet in diameter. When aligned to focus on a single wooden target coated in pitch, a common substance used on Roman ships, the fire ignited within seconds at a distance of roughly 160 feet. In 2005, students at the Massachusetts Institute of Technology attempted a similar test. Using a configuration of 127 square mirrors, they successfully set a stationary wooden boat ablaze under controlled conditions, reaffirming that the principle was indeed plausible, given the right conditions and materials. Though wind, wave motion, and inconsistent sunlight might have limited its effectiveness in a real battle, the concept itself was not only sound but demonstrable. What's most surprising, however, is not the mechanism, but the mathematics behind it. To design such a parabolic array of reflective surfaces, Archimedes would have needed a deep understanding of geometry, optics, and angular projection. These are principles not formally codified until Islamic and European scientists explored optics a millennium later. Yet here they appeared, weaponized in the hands of a man whose inventions still bewilder modern engineers. Archimedes was known to have designed compound pulleys, buoyancy-driven war machines, and even a primitive form of integral calculus. But if the mirror weapon was real, it suggested he had also discovered the principle of solar convergence, focusing sunlight to a single burning point, and applied it in live warfare. So, why does this invention not appear in military manuals or engineering texts of the era? The absence of physical remains is partly to blame. Mirrors, especially polished bronze, degrade or are repurposed over centuries. But there may be a darker explanation. After Syracuse fell, Archimedes was killed by a Roman soldier, despite direct orders from the Roman general to spare his life. Much of his work was lost or destroyed in the chaos. His devices, if not looted, were buried with the city's libraries. Later records from Alexandria mention flaming mirrors used in temple ceremonies, but never elaborate. Any recovered components could have been dismissed as ritual objects or artwork. The military significance of a solar death ray would have been incomprehensible to conquerors who lacked the mathematical framework to replicate it. And perhaps that was the point. A technology so ahead of its time that it became indistinguishable from myth, until the myth was experimentally proven centuries later. If Archimedes could bend sunlight into a weapon before lenses even existed, what other knowledge perished with him in the ruins of Syracuse? The Byzantine Sundial. In 1985, during a restoration project in the ancient city of Antakya, once known as Antioch, Turkish archaeologists unearthed a palm-sized bronze disc buried beneath layers of collapsed masonry. It was intricately engraved with concentric circles, zodiac signs, and cryptic markings in Greek. For years, it was thought to be a ceremonial amulet or astrological chart. But after comparative studies with Roman-era timekeeping instruments, scholars realized they had something far more advanced. A portable sundial calculator from the Byzantine Empire, engineered for personalized astronomical tracking and time measurement. This small disc, dating to the 6th century CE, wasn't merely decorative. It was a functional device designed to calculate local time based on geographic latitude and the sun's position. A remarkable feat in a world without mechanical clocks or digital instruments. At the center of the disc was a pivoting gnomon, a thin rod or pointer, which could be adjusted according to the user's location. Around it were rotating dials marked with days of the year, zodiacal phases, and hour lines, allowing the user to align it with the sun and instantly determine the correct time of day. Further analysis revealed it had an adjustable latitude ring, enabling it to work across a wide range of locations, from Constantinople to Alexandria, possibly even as far as Jerusalem. This versatility suggests it was a traveler's tool, used by scholars, merchants, or military officers navigating vast Byzantine territories. The precision of its markings was astonishing. Many of the gradations were etched less than 0.02 inches apart, fine enough to require tools equivalent to modern dividing engines, which weren't invented until the Industrial Revolution. Even more compelling was the inclusion of astronomical cycles embedded into the design. The rotating calendar disc was calibrated for the Metonic cycle, a 19-year period harmonizing the solar and lunar calendars, and the device allowed users to track lunar phases and major celestial alignments. One reconstructed version could even estimate the date of Easter, a complex astronomical calculation requiring coordination between solar and lunar calendars that baffled Western Europe for centuries. What makes this sundial calculator so extraordinary is its self-contained nature. It didn't require a larger machine, reference tables, or clerical computation. Everything was etched into a tool no larger than a modern smartphone. In essence, it was a Byzantine analog computer, one that could be slipped into a satchel or robe, granting its owner celestial knowledge at their fingertips. And yet, despite its sophistication, it remains virtually unknown. The original artifact now sits in a university archive in Istanbul, unlisted in any public exhibition. Requests to study it are rarely granted, and few high-resolution images exist. Scholars who have attempted to publish papers on it have found their work ignored or rejected by mainstream academic journals, which label it too speculative. Why such resistance? Because acknowledging this device's true purpose would force us to rethink our assumptions about technological continuity. It suggests that portable computing, however primitive, existed more than 1,000 years before the pocket watch, let alone the smartphone. It challenges the linear narrative of progress and implies that ancient knowledge was not merely lost, but systematically buried beneath the rubble of empire, invasion, and dogma. If such devices were once common among the educated elite, what other tools did they carry, and who decided they should be forgotten? The South-Pointing Chariot. In the 3rd century CE, amid the decline of the Han Dynasty, Chinese engineers were developing what would become one of the most perplexing mechanical innovations of the ancient world. Known as the South-Pointing Chariot, this two-wheeled vehicle had no compass, no magnets, and no reliance on celestial navigation. Yet it maintained a fixed pointer that always indicated due south, regardless of the direction the chariot turned. Modern reconstructions confirm that it worked through an intricate mechanical differential, a principle believed to have only been formalized in Western engineering during the 17th century. The chariot's mechanism operated through a gear system connected to the wheels, which adjusted the orientation of the pointer based on the differential movement of the two wheels. If the chariot turned left or right, the gears compensated for the change, keeping the figurine's outstretched arm fixed toward the south. It wasn't magic, it was mechanical logic, executed with wood, bronze, and precision craftsmanship. Detailed records of the device appear in historical texts, such as the Song Shu, Book of Song, describing how it was used in military parades and imperial navigation. The historian Ma Jun is often credited with refining the design. The system was so reliable that it allowed travelers to maintain orientation even through mountainous terrain or heavy fog. It served as a terrestrial guidepost in a world where magnetic compasses had yet to be invented. When modern engineers attempted to recreate the chariot using only tools and materials available at the time, they found the task challenging but achievable, assuming the builders possessed a high understanding of gear ratios, torque compensation, and load balancing. The tolerances required to maintain directional fidelity over long distances suggested that ancient Chinese engineers were not just artisans, they were theorists with a firm grasp of rotational mechanics. However, surviving blueprints or schematics are virtually non-existent. Most modern replicas have been reverse-engineered based on historical descriptions and museum-quality models built in the 20th century. Several chariots were constructed during the Tang Dynasty revival era, but disappeared from the record during later periods of war and upheaval. Some speculate that, as magnetism became better understood, the need for the chariot declined, but others argue that the disappearance of such a clean, mechanical solution hints at deliberate suppression or loss. The South-Pointing Chariot wasn't merely a curiosity. It was the embodiment of applied mathematics and mechanical foresight, in a culture that already pioneered seismographs, suspension bridges, and multi-stage rockets long before Europe. So, why is this invention barely acknowledged in global engineering history? Because if a civilization could master differential gearing over 1,000 years before it was discovered in the West, it forces uncomfortable questions about the true origin of modern mechanics. It dismantles the myth of a linear technological evolution and suggests something more chaotic, or perhaps more controlled. If China had differential navigation in the 3rd century, what other systems did they build that we still haven't rediscovered? The astronomical ring dial. In 1936, during the cataloging of overlooked artifacts at the Ashmolean Museum in Oxford, a small bronze instrument caught the attention of a young curator. It had been mislabeled as a sundial fragment and left untouched for decades, but upon closer inspection, its complexity defied that simple designation. It wasn't a sundial, it was a ring dial, a pocket-sized astronomical computer that could determine time, date, latitude, and even solar declination based on the position of the sun. Its origin, likely Greek from the 2nd or 3rd century BCE. The device consists of 3 concentric rings: the meridian ring, the equatorial ring, and the declination ring, all hinged so that they could fold flat when not in use. When properly aligned, sunlight passing through a pinhole would cast a beam onto the calibrated inner surface, indicating solar time and seasonal position. With just basic adjustments, the dial could reveal what modern navigators would call longitude correction or solar noon, concepts not believed to have been fully understood until the age of exploration. Unlike a fixed sundial, the ring dial was portable and self-calibrating. Travelers could adjust it based on their latitude, thanks to detailed angular notations engraved in Greek letters along the inner curves. Even more impressively, the markings incorporated leap day adjustments and zodiacal shifts, hinting that its users understood the precession of the equinoxes, a concept formally introduced by Hipparchus, but rarely seen in practical instruments. Testing conducted by astrophysicists at the University of Athens in 2009 revealed the device's remarkable accuracy. When aligned correctly, it could track solar movement within an error margin of 1.5 degrees, enough to determine the time of day within 10 to 12 minutes, even by today's standards. The reconstructed dial functioned effectively across a wide latitudinal range, confirming its use as a traveler's navigational aid. But for all its elegance and sophistication, this device, and others like it, never made it into widespread use or historical record. Why? Some believe the ring dials were the tools of an elite scientific class, passed down through oral instruction and kept deliberately obscure. Unlike the Antikythera Mechanism, which was large and elaborate, the ring dial was personal, small enough to wear, yet powerful enough to chart the heavens. Others argue that the rise of empire and dogmatic religion gradually eroded the empirical curiosity that produced such devices, casting them into disuse or destroying them altogether. The few that survive are scattered across European collections, mislabeled, misunderstood, or dismissed as novelties. Replicas are sometimes sold as curiosities, ancient sundials for collectors, without any mention of their potential as analog computers. And yet, they may represent the most direct link between ancient stargazers and modern navigators. If Greek scientists could carry the cosmos in their pocket, mapping the sun's journey with nothing but brass and geometry, then what else might they have known, recorded, and quietly taken with them into the shadows of history? The Roman Dodecahedron. In 1739, a peculiar bronze object was unearthed in a field near Mainz, Germany. 12 flat pentagonal faces, each with a circular hole in the center, arranged into a perfect dodecahedron. Measuring about 3 inches in diameter, it had no inscriptions, no symbols, and no written reference in Roman texts. Since then, over 130 similar dodecahedrons have been discovered across Europe, from Britain to Hungary, always within the bounds of the Roman Empire, always made of bronze and always undocumented. Their purpose? Officially unknown, but their construction suggests a level of geometric utility far beyond mere ornamentation. Each face of the dodecahedron features a hole of varying diameter. The sizes are not random, they follow proportional relationships. Experiments by archaeologists and optical engineers have shown that when 2 opposite holes are aligned and viewed through, The resulting field of view changes depending on the size of the aperture. Some researchers believe the object functioned as a rangefinder, an optical tool for estimating distance to known targets, such as banners or siege towers, by matching the angular size of the viewed object to the hole's diameter. This theory is supported by experimental archaeology. In one study, participants used 3D printed replicas to measure the distance to standard objects placed at varying ranges. The dodecahedron consistently provided distance estimates within a 10% margin of error, comparable to modern low-end rangefinders. Another hypothesis suggests that the device was used in agriculture, particularly in planting cycles or calibrating sowing patterns by casting light and shadow through the holes at specific solar angles. Others propose it was a surveying tool, helping Roman engineers align structures with astronomical bodies or ground features. The precision with which the holes were cut, sometimes within 0.1-inch tolerance, indicates intentional craftsmanship for functionality, not decoration. Stranger still is the distribution pattern of the finds. They've been recovered primarily in northern and western provinces, not in Italy, suggesting regional use among Roman legions, or by specialized engineers or officers. Some were found in military camps, others in graves. None have ever been recovered in contexts associated with mass production or widespread civic use. So, why were they never described in any surviving Roman literature? One possibility is that the dodecahedron was a classified military tool, its function passed down through oral instruction or tightly held within engineering cohorts. Roman military manuals were notoriously secretive, and many were lost during the decline of the Western Empire. Another theory posits that the object's practical function was deliberately erased by later authorities, its association with geometry, optics, or even astrology making it suspect during the rise of Christian orthodoxy. Today, most museums list the Roman dodecahedron as an enigmatic artifact, offering theories ranging from candlestick holder to dice. Visitors walk past, unaware they may be looking at a handheld optical computer, capable of range finding, solar calibration, or astronomical alignment, all without a single moving part. If the Romans had access to such portable geometric instruments, what does it say about their understanding of optics, projection, and spatial measurement? And why has the silence around them remained so complete? The South-Pointing Spoon. In 1950, deep within the archives of the Palace Museum in Beijing, a curator uncovered an object long mislabeled as a ceremonial ladle. It was crafted from a single piece of lodestone, a naturally magnetic mineral, and shaped like a shallow spoon with a curved handle. Nearby lay an ancient bronze plate, inscribed with the 8 cardinal trigrams of Taoist cosmology. When placed on the plate's polished surface, the spoon rotated smoothly until its handle invariably pointed south. What had been dismissed as ritualistic art was, in fact, one of the earliest magnetic navigation tools in human history, the South-Pointing Spoon. Historical records trace its origins to the Shang dynasty nearly 3,000 years ago. This predates the Western compass by at least a millennium. The South-Pointing Spoon didn't use any electricity or gears. Its power came solely from Earth's magnetic field. It functioned with surprising consistency, providing directional orientation without celestial input, a revolutionary tool in a world guided by stars and landmarks. Unlike the later magnetic compasses of the Song dynasty, this device had no floating needle or liquid suspension. Its design was purely analog. The spoon's belly rested on a smooth, flat bronze plate, allowing frictionless motion. As long as the lodestone retained its magnetism, which it could for centuries, the spoon would align itself with Earth's magnetic field, its handle always swinging to the south. This gave travelers, generals, and surveyors the ability to navigate even in thick fog, dense forests, or moonless nights. But its significance extends beyond mere direction finding. Ancient Chinese texts like the Lushi Chun Qiu describe the spoon not just as a navigational aid, but as a symbol of cosmic harmony, aligning human movement with the forces of heaven and earth. The tool's dual nature, both practical and spiritual, likely contributed to its limited spread. While magnetic awareness was known, the full potential of the spoon may have remained confined to elite scholars and geomancers. In modern times, experiments using authentic lodestone recreations have confirmed the spoon's functionality, When placed on smooth bronze or even polished glass, it aligns within plus or minus 3 degrees of true south, a level of accuracy comparable to many medieval compasses. Given the simplicity of its construction, this suggests a profound understanding of both magnetism and material properties, at a time when most civilizations lacked even the concept of magnetic poles. Yet, just like many ancient instruments, the south-pointing spoon has been largely omitted from global narratives of innovation. It is rarely discussed in standard histories of science or engineering. Most students learn that compasses were first used by European sailors in the 12th century, not Chinese scientists in the 11th century BCE. Museum displays often describe the spoon as symbolic, glossing over its mechanical genius. Why? Because acknowledging its place as a fully functional, prehistoric magnetic device reshapes our understanding of technological timelines. It forces us to accept that ancient China may have discovered and applied fundamental physical forces long before they were officially understood. It also challenges the notion that progress follows a single linear path, when in truth it may rise and fall like dynasties. If the south-pointing spoon could provide reliable navigation without a compass needle, without gears, without electricity, what else did its inventors know about the invisible forces guiding our world? Conclusion: these 10 devices, scattered across time, continents, and collapsed civilizations, reveal a disturbing pattern. Our ancestors may have known far more than we are allowed to remember. From the precision gearing of the Antikythera Mechanism to the magnetic balance of the south-pointing spoon, each artifact presents a riddle that modern tools can replicate, but modern history often refuses to acknowledge. These are not speculative tales or whispered legends. These are physical objects, tested, measured, and in many cases, reconstructed, only to be quietly filed away in museum basements, mislabeled, or ignored. This isn't random, it's a model of selective recognition and intellectual suppression. We see it in how artifacts are reclassified from technological to ceremonial, in how ancient tools are written off as accidents of geometry rather than deliberate innovation, in how researchers who pursue these anomalies are denied funding, blocked from publication, or labeled fringe. This is not oversight. This is a pattern of control, academic, institutional, and historical. And with every artifact buried, mislabeled, or destroyed, a potential breakthrough for humanity is lost. Devices that could have advanced our understanding of timekeeping, navigation, or even energy generation by centuries are reduced to curiosities. The Baghdad Battery might have led to a pre-industrial electric revolution, the Archimedes Mirror to energy weapons. The ring dials and sundials could have taught generations to track the heavens by hand. What we call primitive may, in fact, be the remnants of erased progress. It is not just a loss of tools, it is the loss of opportunity to learn, to replicate, to evolve. And perhaps more troubling is that the mechanisms of suppression are still in motion. Grants denied, permits revoked, artifacts locked in vaults. The guardians of official history maintain a version of the past where breakthroughs happen only when allowed, and only in the right direction. If these ancient devices truly functioned, and evidence shows they did, then the question is no longer whether they existed. The question is, why did someone go to such lengths to make sure we forgot them?